All right, good afternoon, everyone. Thanks for coming to this talk on concurrent maintainability. It's part of the ACF workstream. My name is Jabari George with JM Gross Engineering. This is Ryan Orr with the Uptime Institute. So before we start, I'm just going to give a brief overview in terms of the background of this workstream and where it came from. So the industry, a lot of you all will be very familiar with concurrent maintainability for air-cooled deployments, because most likely because you would have to interface with the Uptime Institute's tier standards. Those are two different things, and we'll get into that. But with the advent of the increased interest in liquid cooling over the last 2 years, you were getting a lot of feedback from the community in terms of questions and concerns around how you could accomplish concurrent maintainability with liquid cooling in a data center. So we collaborated with the Uptime Institute and OCP members all along the value chain to answer that question. How can you design and deploy a liquid-cooled solution in a data center? That was the basis of this work stream, getting that feedback from the community. So in the white paper, you're going to see considerations toward that end. Okay, so that's just a basic background. I'm going to hand over to Ryan now, and he will go over the history of concurrent maintainability.
Thanks, Jabari. I'd first like to start by sort of making sure that we're baselined on what we mean when we talk about concurrent maintainability. It's a common term. I'm sure everyone in this room has heard of it, but it has a sometimes uncommon misunderstanding across the industry. Misconceptions, myths are rampant. So it is the ability to isolate for removal, maintenance, repair, upgrade, any capacity component or distribution pathway without impacting power or cooling or telecommunications to the IT equipment, right? That definition is derived from the idea that data centers have 10, 20, 30 plus year life cycles, and we need to be able to do regular maintenance to the equipment if we're going to be keeping it in like new condition and meeting those high level resiliency objectives that are supported by those data centers. It's also important to identify that when we look at concurrent maintainability and we talk about redundancy requirements and things like that, we're focused on a requirement where there's permanently installed redundancy to those equipment pathways. Now, the definition of concurrent maintainability is in part intended to promote safe and efficient maintenance requirements. And if we're doing that, we want to have that permanently installed redundant pathway or capacity component to facilitate that maintenance. Now, why are we having this conversation now? Liquid cooling's not a new technology. It's been around for a long time, both in the data centers and in other applications. But what is different is that historically, liquid cooled until more recent deployments has been primarily supporting IT applications that had a high tolerance and allowance for downtime. You know, HPC research, maybe it can go down for a week, a year, or a week, a month, and that's okay. That's in line with that objective for that IT equipment. But as liquid cooling adoption increases and as IT resiliency requirements also increase, we need to be very thoughtful and careful about how we think about achieving the resiliency requirements with liquid cooling potentially being a significantly more mainstream cooling solution. One of the things that we see is, one of the things that we'll be talking about in the white paper is the importance of aligning your cooling system design with the IT objectives, right? There's more than one way to be concurrently maintainable. It's not a prescriptive outcome. There's multiple ways to achieve that. It's really important that we work together between facilities and IT to understand what the IT performance requirements are of that particular application. For example, do I need 24/7 uptime at the rack level? Do I not have a redundant hardware instance of that IT application? Or do I need concurrent maintainability at a system level? Maybe I have 2 racks in 2 different data halls in the same data center, or maybe I have them in 2 different availability zones. Being able to map and understand that will be key to deciding how we're going to implement liquid cooling in a concurrently maintainable way. So the technical paper that Jabari is going to discuss the framework for here in a moment, it really is focused on achieving sort of that worst case, most difficult situation, which is achieving concurrent maintainability at an individual rack level. But it's absolutely possible to have other ways of achieving that. Like I said, for example, if you have an array or cluster of racks and only half of those racks are required to be able to accomplish the compute and application that you need, that may be a concurrently maintainable way of implementing DLC if the A racks and the B racks are supported by separate DLC systems. So as we move through that, keep that in mind.
Thanks, Ryan. So in the white paper, we went through a sequence of activities. The first of them was to define the boundary between the facility and the ITE. So where is that line of demarcation? Now that's going to be different for each topology, as you can imagine. But what we wanted to get across in the presentation is what was the philosophy behind this exercise, right? So the boundary would establish what components of the liquid-cooled system would need to be concurrently maintainable. And as we were doing that demarcation exercise, the question was always the same. In terms of design, can this component be maintained without bringing down the system or without downtime? And so those schematics you'll see on this side of the screen, these are not concurrently maintainable, but that was the kind of schematic we would be looking at in the meeting. And sometimes a vendor would see a line right through their solution, and they'd wonder what was going on. And you have to remember that the vendor's liquid cooling solution is just one part of the overall cooling system. So if you are taking a concurrently maintainable approach to your facility, you need to look at everything on that system, not just your solution if you're a vendor. So that's the point that I was trying to make in that third point there. And then finally, as Ryan would have mentioned, the way you choose to operate your facility also has an impact. If you have two systems that are N+1 or duty standby, and you are basically using them to run the same workload, and one goes down, and you have an automatic switch, do you really need to have two, both of them be concurrently maintainable? So those kind of operational nuances are things that would impact your line of demarcation as well, and we acknowledge that in the discussions that we have. So further than that, so I would have mentioned that air-cooled data centers are what people would be accustomed to. But as you bring the facility and the rack closer together, or the facility and the chip in some cases, you have to, it's no longer just considering the rack to be the handoff point, and you just think about your CRAs and your cracks. Now you have to look at all the complexities that are introduced by having a liquid-cooled solution. Now, generally speaking, you're going to have to, for the entire TCS, have a concurrently maintainable solution. So you're going to have to be looking at redundancy for your piping and your fittings, etc. That may be hard for some people to solve, but if your philosophy is concurrent maintainability, this is just a reality. There are nuances again, but that's something that we've been seeing as just a reality of the situation. The other thing is that as you're making those lines of demarcation, you have to understand what you're asking of the people responsible for the components on either side of that line. So if IT personnel are now responsible for liquid-cooled equipment, they're going to be doing activities that are typically associated with the facilities team. So they're going to have to collaborate really well with that facilities team in order to accomplish the goal of the organization. So as we looked at each of the topologies, we looked at the opportunities and challenges. And in the white paper, we actually go through various considerations for each topology. We attempted to do that initially for this presentation, but we couldn't do it justice based on the information we had in the white paper. So instead, what we are doing is looking at the unique aspects of each liquid cooling topology that would build a framework for making the considerations that we have. So in the case of immersion, we looked at the having an external versus an internal CDU, or chassis immersion versus tank immersion. So those were the kind of the scenarios that we looked at. And in terms of the unique characteristics for immersion cooling, the fluid would be a single point of failure, meaning that if for some reason your fluid became contaminated, you virtually lose your cooling, right? So that is one unique aspect that you need to take into consideration when you're doing, if you're doing a concurrently maintainable design. Also, the fluid also has another characteristic, which is that it is the only topology in which you have constant contact with the air. So you need to be aware of that you need to manage your indoor environment as part of that concurrently maintainable philosophy, because it has a potential to impact your fluid that it's in contact with. Thirdly, the liquid volume in the tank it can change very quickly as you add and remove components. And immersion, as we all know, it works so well because of the contact between the liquid and the components. So if you lose that contact instantaneously, then you defeat the purpose of it. So you need to have really good level control for your tank solutions, and that is going to feed into your concurrently maintainable philosophy. Finally, and it's a really good aspect of immersion cooling, it shows up in the Rev 3 of the requirements document for immersion on the OCP, is the thermal ride-through. You have a really good, compared to air, really good thermal ride-through available to you by virtue of the properties of the fluid. So that really helps if you're looking at maintenance. So in terms of the cold plate, we again looked at the external versus internal CDU in designs. And in terms of the unique aspects, the cold plate, by virtue of just how it is designed, or it's not practical at least, to be redundant. So you can consider that another single POF, but that's an aspect of the cold plate that you have to accept. Another is that in most applications that we've seen, there is a percentage of heat that is liquid cooled and a percentage that is still air cooled. So you need to manage both the air and the liquid cooling for concurrently maintainable designs. Finally, the coolant filtration, because of the bore sizes and the clearances involved with cold plates, you need to pay really close attention to your filtration as compared to the other liquid cooling topologies. And then we talk about cold plates as one component, but you have to remember they're part of a closed loop. So you have to look at your manifolds, your CDUs, etc., and as part of your concurrently maintainable solution. Finally, door heat exchangers, again, external versus internal CDUs. The good thing about door heat exchangers is that they are comparable to traditional air-cooled designs. Even in design, you can model them with CFD as a CRA, because they're just cooling back down to ambient. So that's really good if you're choosing to go with those. Again, there's a single point of failure because it's not really practical to have a redundant door. But if your door does go down, you can use the facility as to make up for that lost capacity by just opening the door and maintain your operation while you do your repairs. Doors can be active or passive, so you have to be reminded that the fans in the active door would need to be involved or catered for in your concurrently maintainable philosophy. And then in terms of integration with cold plates, that's a possibility with the heat exchangers, but then you have to consider both. You have unique considerations for both of those types of topologies. Finally, what we're talking about now in the white paper is design and operation interface management. So on the design side, those complexities introduced by liquid cooling, what do you need to look out for in design that you may miss? So the example I always give is, if you have drains and vents all along your TCS system and in your rack, who's responsible for ensuring that those are installed? Is it the consulting engineer? Is it the integrator? We can't tell you that, but we can tell you that's something you need to look out for. And then on the operation side, as you see there, like what happens if I push this button or close this valve? It's about managing the understanding between the IT and the facilities team so that they know what the impact is of doing maintenance on a particular item. And everyone uses the same document. So that's what we're trying to develop here with this spreadsheet. It's just a simple tool to manage the communication between the teams.
One of the interesting things about this work stream is that when it started, and Jabari invited us to participate, we didn't really intend to get as much into the application. We mostly wanted to stick to, trying to define concurrent maintainability and what that means for these various types of direct liquid cooling systems. But there's been a lot of industry folks coming to either us directly or attending those sessions saying, I need to understand how to integrate these into my existing data centers, right? A lot of people are just starting to adopt or think about trying these various types of technologies. They're not ready to go build a multiple megawatt data center that's 100% liquid cooled. They want to try it and kick the tires out in their own existing data center first. But they have one of two problems. They're either saying, I don't know how to make it concurrently maintainable, and I don't know how to integrate it with my existing site, or I have a site that's already concurrently maintainable, and I don't necessarily need concurrently maintainable direct liquid cooling, but I don't want my deployment of direct liquid cooling to impact my existing data center. What do I do? Now, I don't think there's a prescriptive answer for any particular client. Every data center is different depending on what type of primary heat rejection system is currently being used. But we do think that there's a process of evaluation that people should go through. And this is something that we are going to be getting into the technical paper about based on feedback from participants in the work stream. But some examples of this, like does my liquid cooling system reject 100% to the liquid, or is it a mix of air-cooled and liquid-cooled? If there's a significant chunk of air-cooled heat load being rejected, that may have significant impact on how you do your space planning, where you physically want to locate your liquid-cooled racks, and whether or not they can even go in the same space as your existing 100% air-cooled racks. Do you need to share your facility cooling system, right? What are the requirements of the direct liquid cooling system you're trying to implement? Do you need 15 degrees C water? Do you need 32? What are you supplying to your perimeter raised floor crawl units today? Do those numbers align? Are they significantly different? Those are the sorts of questions that people need to be asking themselves and saying, and to help them through that decision-making process of how to implement and integrate direct liquid cooling in an existing 100% air-cooled data center.
So it's the last slide here. It's just a call to action. We want to make sure that the white paper that comes out of this is useful to the community, and the best way to do that is by getting your responses, your expertise, your experiences, and collating that into this white paper. So I would have reached out to a number of people, gone to different groups. It's important that we get this current feedback and this current participation to make sure that whatever comes out of this, you all can use it from day one. Okay, so we invite you all. Here's the information. You can reach out to me or any member of the Cooling Environments leadership if you want to participate. And we're going to try to get this wrapped up by this year, at the end of this year, but you are free to participate before then. So thank you. That's the information, the links, if you want to get more information. And that's it. If you have any questions, feel free. Oh, sorry, you were taking a photo. I said someone's on this mic.
Oh, you mentioned the filtration is critical for the loop.
Yeah.
So do you have a spec, like the size of micron you want to recommend?
So we had that discussion in the work group, and what happened was, as you can imagine, there are different types of cold plates. You have some that use chilled water, some use coolant that I can't remember what Zuzako uses. You also have some coolants that some systems that are thermosiphon with no moving parts. So it really depends on what your application is that would influence the micron size. I can't, it depends on the vendor, and each one of them had a different recommendation. But I will say, every time you engage a vendor that's going to issue you a cold plate, that you should make sure that that is in the spec or in the maintenance manual.
Are you going to include requirements for cleanliness and how to purge water and change fluids out, meaning pulling all of it out of the manifolds and the cold plates if needed in any of the loops? And I think that goes for both the primary facilities water side and the technology cooling system.
So you mean, like, if you have to replace, you're talking about any topology, right? So if it's immersion or cold plates.
Focused on cold plates.
Cold plates, yeah. Well, we did have that discussion as well. There was a lot of back and forth. But like I said, there are different technologies. If you have a thermosiphon, there's no interaction that would cause you to have to replace your fluid because you have no moving parts or anything like that in there. We did talk about making sure that you can drain. I'm not sure if I'm answering your question, right? So
Yeah, I'm thinking about any contamination in the loop with regard to shavings or anything that might be in the manifolds for some reason
Yeah.
during either the installation process or during the manufacturing process.
Oh, sorry. Okay, yeah. So if you're talking about commissioning, yeah, we've had that discussion as well. We have a micron recommendation. I believe it's 5, but I'm not sure. But once again, if you're going with a particular vendor, they'll tell you when you're flushing at initial startup what size filter you're going to need, right? When we get into the realm of making recommendations, it gets really kind of dicey because everyone kind of has their own special set of considerations. And it's really difficult to go down that path. I will say, though, that the cold plate group has released some specs for ethylene glycol or propylene glycol and chilled water. So, and they have some information, there's some recommendations. So you could check that out.
Okay, thank you.
And just to add, I know we're almost out of time, but where that conversation actually started in the work stream was we were looking at whether or not there was the potential that filtering systems, due to how they're used in these systems and their criticality, which what you're alluding to, whether or not they would actually have to be concurrently maintainable themselves, the filtering systems. And the paper's not going to require that or recommend that, but it will have recommendations around commissioning and initial startup and installation. Thank you.
Thanks.